this kind invitation, and it's a great pleasure to give such a talk. I got to know that it's probably related to Sunday morning and Prof beams yesterday, but I hope actually more people come in and get to hear things. I start with this question that what we are all made of. Okay, this question has been there. This more than a scientific question. It has always been there since the start of mankind, and we would like to know how the constituents that make us, they form about us, how they actually contribute to various properties that we see about ourselves. And this is what I am going to talk about. And the main purpose is I will take you through some sort of builds in pedagogical survey, so that we reach a stage where we can start understanding what happens inside a nucleus or what happens inside the nucleons. So nucleons are generally basically protons and neutrons are typically referred to as nucleons. So what happens inside nucleons is the thing that we want to actually reach towards. Okay. So in this case, I call this actually a modern understanding of constituents, because you see there are already very many non-scientific statements, non-scientific assumptions that we are made of water, air, etc., etc. But these are all non-scientific, while the first scientific way of understanding what we are all made of was sort of proposed by John Dalton. Of course, I am not a historian, so if you actually look back into history, etc., there exists other scientists in the past, even in India, actually people have proposed that the smallest particle that we are made of is called as an anu or atom. Okay, and John Dalton is sort of the point when people start understanding that this is some minute quantity which has properties that we see around. And he proposed that we are all made of small indivisible spheres, and this green rather than the other one. And he claimed that actually these indivisible spheres cannot be created or destructed, and two such spheres of the same element will have the same properties. That's why we say that they are identical, and if they are different elements, they will have different properties. And the combination of various of these elements will form compounds and molecules. By the way, I was informed that actually the audience will be a spectrum of various students who may or may not have exposure to various of these things. So in case I have made my slides to be as basic as possible, but what is basic for me will not be basic for you. So, and I have also given the freedom that I can choose the format of the talk. So in case if you have questions, please feel free to interrupt me. Okay, so just don't let me go ahead even without understanding. So just interrupt me when you don't understand something. So he claimed that actually combination of elements will give us compounds or nucleus, or compounds or molecules. While later on, around 90 years later, J.J. Thomson, after his discovery of electrons, claimed that you see actually these are not really indivisible spheres, they are indivisible spheres, they have some inner structure in it. And he claimed that given that we get some negatively charged particle out of these indivisible spheres, they are probably made of some big positively charged lump, and electrons are scattered inside it. He did not really give much of a scientific detail into it. He just told that actually these are divisible spheres, but positively charged spheres with electrons scattered, fixed and scattered in that sphere. Okay, so this is typically referred to as the plum pudding model. While these actually still have defects in it, and sort of things started getting more and more clear when Ernst Rutherford did this famous gold foil experiment. I assume you may have all heard of gold foil experiment in your high school, where in this experiment Ernst Rutherford, what he did is he actually tried to scatter alpha particles. Alpha particles are basically helium nucleus, which has two protons and two neutrons in it. So basically they are positively charged particles. He scattered them over a gold foil. Okay, and he found that actually most of the alpha particles that he actually blast into this gold foil basically passes through, while relatively small amount of alpha particles just get deviated, and even smaller number of them actually basically gets directly pumped back. Okay, so this basically gives us the idea that this plum pudding model is probably not the case. If it was really plum pudding, it may have all passed through cannot have actually these kind of deviations like once in a while. And also it is very difficult to actually get this kind of reverting back kind of beams. So he claimed that this is highly likely that the positively charged thing is basically a concentrated, heavily concentrated nucleus or nucleus or nucleus. You may have heard about this scale comparison in various videos, YouTube, etc., where they say that if you take an atom, the nucleus is basically some cherry sitting in a big football field, football stadium, right? So there is so much concentrated nucleus, positively charged nucleus, while electrons are revolving around them. There remained a question that if the electrons are revolving like that, we know that the electron can easily lose energy. If they are revolving around this positively charged nucleus, they can lose energy and they can just fall back. And we have been living for like millions of years, billions of years, by having these electrons just fallen into the nucleus. Okay, so this was a question that was not clear then, but at least based on his experience, it was clear that the nucleus is basically a very concentrated point-like object inside this big atom, the electrons revolving around it. Later, in fact, actually around those, even before the experiment itself, we already knew that if you just take a gas of hydrogen atom and you put white light into it, there are actually several spectral absorption or emission lines, depending on what kind of experiments you do, whether you actually try to actually make the hydrogen atom absorb or emit, or whether the hydrogen atom is heated up to the various energy lines. Depending on that, you get to see either absorption or emission lines. And this was already, people have already tried to explain why these kind of spectral lines were coming. And Niels Bohr first gave a more concrete idea of why these kind of spectral lines happens. And this was also a solution for this J. Thomson's model, Rutherford's model, where Niels Bohr argued that electrons cannot arbitrarily revolve in arbitrary orbits. They can actually revolve only in certain specified orbits. Okay, and these specified orbits are given in terms of coefficient, constant called Hilbert constant. And these orbits have definite sizes and they have definite energies. And if you actually try to compare the energy difference between various of these energy levels, you see that they are basically corresponding to various of these spectral lines. So he sort of managed to explain various of these spectral lines that were observed based on the energy levels of hydrogen atom. And this is what he said. So electrons move in different orbits. They can actually jump from one orbit to the other by gaining or losing energy, depending on whether it is actually going to a higher energy level or a lower energy level. And thus he could explain the hydrogen atom emission and absorption spectra. This sort of give a picture that this is sort of like a planetary model of atom. Okay. But he still could not, like I said, I am not a historian, so I may not be as precise with the details of what I am saying. Whatever I am saying is based on whatever I have learned from my students and graduate schools, etc. So I might be inaccurate in certain statements of how things were actually discovered at different point of time. But one of the things that I have actually realized is that when I read through various of these developments is that although Niels Bohr gave this kind of explanation for why these spectral lines were observed, he could not really argue why these electrons can only exist in specified orbits. What is special about these specified orbits were not clear even with Niels Bohr's explanation. This was sort of argued, or this was sort of explained after Schrödinger and many others who were actually using these quantum mechanical ideas, argued that these specified orbits are actually determined by quantum mechanics. So if you have an electron revolving around a hydrogen nucleus or a proton, then there are only regions of probability. They are not even orbits, they are basically regions of probability where the electron can exist. Okay, and the classical case that we thought actually, at least in Niels Bohr case, actually he said actually there are orbits. And the peak point of this peak regions of probability is basically determined by the classical case. Okay, and the distribution of this probability distribution is determined by quantum mechanics. This is what actually Erwin Schrödinger argued. I assume that you may have had some exposure to these things, at least in some videos or somewhere, if not in the classes. But are we done with the understanding of atom? No. There were other experiments where actually people found that there are certain energy levels, like 2p, 2s 1/2 and 2p 1/2. Here I have pointed it out. And in the experiments, means based on the theory, based on plain quantum mechanics, it was argued that they should be degenerate. What do we mean by degenerate? Their energy levels should be same. The value of the energy of those levels should be same. They should not have different energies, which means that if the electron transit from 2s half to 2p half, they should not release any photon, right? Because there is zero energy between them, as per standard quantum mechanics. But in the experiments, it was found that actually there is a small energy difference, which was not clear why that energy difference happens to come or where it is coming from. This was actually observed by Willis Lamb and Robert Rutherford in 1947. And this was sort of a whistleblower for the development of something called quantum electrodynamics. What that means is actually here, this energy difference basically comes from some self-energy correction of electron. What do we mean by self-energy correction? An electron has a negative charge, which means actually the surrounding medium of the electron can get polarized because of this electric charge, which means that there is some, it can also happen that there are some new electrons. Because of some quantum fluctuations, you can have some electron and positron created from the vacuum. And these kind of corrections, these kind of vacuum fluctuations will give corrections to the interaction strength of the system, and that effectively leads to some energy difference here. Let me not speak of those details, but the main message is that we needed quantum electrodynamics to explain this energy difference. Okay, the main message that I am actually trying to get at is that as the time progresses, as our understanding of experiments progress, as other experiments give us more and more details, theoreticians give more and more ideas how to actually interpret these experimental observations, we get better and better understanding of what is going on with the systems, or what is going on with the constants that we are made of. Okay. Today we know actually a big periodic table of atomic elements. We do have quite some understanding of how they are actually structured, what is the energy level structure of various of these atomic elements. And not just about atomic elements, we also know the landscape of nucleus or nuclear landscape, where we know that different nuclei are stable in different regimes, why they are stable, etc. All from some so-called effective field theory model. Okay. Now, once again the question comes, are we done with our understanding, or can we actually go more? Can we further break down things and try to understand how these nucleus are made of, or how these nucleons are made of? And this is what I am trying to get at. Okay. Now let's take a proton or a neutron. I hope that you may have heard of quarks degrees of freedom. A proton is not to be made of 2 u quark and a d quark, and a neutron is made of 2 d quarks and a u quark. And each of these u and d quark has their own electric charges. If a proton is made of 2 u quarks and a d quark, they are basically the main source of interaction is electrodynamics or quantum electrodynamics, if you want to actually claim it so. And given that we have 2 positively charged, 2 u quark means actually they basically have the same charge, they should repel each other, and their repulsion should be compensated by any attraction due to the d quark, which has an opposite charge, okay, to make them stable. Otherwise the proton cannot stay stable, which means plain electrodynamics cannot explain the stability of proton. Right? You have a question? Okay. So plain electrodynamics cannot explain the stability of a proton. So here I did not really say anything about what is going on inside a proton or neutron, but you can also say in this way. So you take a deuteron, even if you don't take the internal structure of proton or neutron, but you can just take deuterium atom or deuterium nucleus, neutron nucleus. You have a proton and a neutron inside it, and it is known to have a binding energy 2 MeV. Proton has positive charge, neutron has neutral charge. How is it staying bound? Right? That means there is some other interaction that we don't know of at the moment that is driving the stability of neutron. Okay. So it was around 1932 actually Heisenberg proposed that there is some additional quantum number. This is not the final answer for why this is stable, but this is sort of a breakthrough for understanding there are other degrees of freedom that we are unaware of at this point of time. which we can introduce and try to explain. There are these degrees of freedom and there are these new interactions that we are unaware at this point that drives the existence of these kind of stable heavy nucleuses. Okay. So Heisenberg proposed there is some other quantum number called isospin quantum number, or else he said that actually you can consider there is this isospin quantum number between proton and neutron has a downspin in that new quantum number. Let's say this quantum number is half, and the third components are say minus half and plus half, and you can actually form various different kind of structures. And this way you can argue that neutron has a spin 1, etc. Let's not go into those details. Now the same way, this same idea can be extended to protons. I already said that proton is composed of 3 quarks, 2 u quark and a d quark. A neutron is composed of 2 d quarks and a u quark. And we also now know that from various experiments and other indirect knowledge, we know that there are 6 different kind of quarks: u, d's, charm, straits, top and bottom. Okay. And we would like to know how these quarks are actually building protons and neutrons. So first thing that is clear is that protons and neutrons are not basically fundamental particles. They have some composite nature inside, and we would like to know how this composite is, or what is the kind of compositeness inside there. So this was first revealed by deep inelastic scattering experiments at the Stanford Linear Accelerator Center. And the same isospin symmetry that was argued by Heisenberg could be extended to u and d quarks, where you can consider u has an upspin and d has a downspin, and in this way you can easily extend back the same quantum number for neutrons and protons. Okay, so let's not go into the algebra, but you can extend it. Now, more interesting part is actually, given that you have 3 quarks in it, you can consider a theory which has sort of 3 equivalent electric charges, not really electric charges, but some other charges, 3 charges, a 3 color charge. Since you don't know what is that new charge, they named it color because sort of color is an easy thing to start with here. They call it color, a 3 color charge. Okay, and the combination of these 3 colors make it totally white, which means the total object is colorless, while individual quarks have some non-trivial color. So this way you can form proton and neutron in a theoretical sense, naive theoretical sense. And this theory is referred to as quantum chromodynamics. Dynamics is trivial because we are all trying to understand what is the dynamics going on inside. System is a quantum system. Chromo because we named it color. This degrees of freedom is referred to as color. We call it quantum chromodynamics. We had quantum electrodynamics earlier. Now we have a new theory that is named as quantum chromodynamics. And all these proton, neutron, and many other similar kind of particles are referred to as hadrons. And they are all color neutral degrees of freedom. And hadrons is the name for the family of proton-like excitations. Okay. Now, yeah.
When you say that 3 colors, can we consider it like just 2 different charges and we're taking linear combination of those charges in the...
No, sorry. No, these are actually, you can actually think of this way. So, you have a positive and negative charge in electrodynamics. That is equivalent to 1 charge in the quantum chromodynamics. You have 3 equivalent stuff. Only thing is they are correlated with each other because they are, these are some, yeah.
So you are saying that those 3 charge colors, can we like have combination of those colors? Like, can we say?
You can think of this way. So when you are, probably white chalk is better, right? Your electrodynamics is 1 dimensional, 0 charge, which is plus, minus. Okay. I put a new dimension. I put another new dimension. Okay. So this is actually just plain electrodynamics. Theory of electrodynamics. Now I have actually a new theory where it has actually 3 dimensions. And I can call this red, green, and blue. And the equivalent negative counterparts are cyan, yellow, and forgot the third color. I don't really use it. I can actually do it this way. So I can say this is anti-blue, this is anti-green, this is anti. Okay.
So any linear combination works.
You can actually form any combination. So if you take red and an anti-red, it becomes colorless. Okay.
And
if you take red, green and blue together, it also becomes colorless. This is something that we have.
Yeah, so it just become one plane.
Sorry?
Doesn't this just become one plane?
No. It's actually a three-dimensional system.
I mean, like if you are saying if you portion it out by red plus green plus blue is equal to
Yes.
zero,
Yes.
won't it just become a plane?
Yes, you can actually say so. I don't really like to think in terms of a plane here, but you can say so, yes. But you see, actually, proton and neutron are not the only hadrons that you can form. Like I said, if you actually take a system of a quark and an anti-quark, which has a red color and an anti-red, that is also colorless. Those kind of particles are called mesons. Okay, they just do not form together. You can also consider objects which are like quark, 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 or anti-quark. So I said actually this is colorless. I said this can also be made colorless. You can actually of course construct colorful objects as well here, because blue theory allows you to do that, but real world doesn't allow colorless objects, at least in the regime where we live. Okay, so these are all colorless. So if you actually consider RGB, you should actually do this thing. This should have R bar, okay, and this can be RGB, you can actually do R bar. It's too naive a description. Actually, group theory says that various linear combination is the actual form of this color structure. I don't want to say this. Okay. Okay. All right. So now if you can understand this theory of strong interaction or quantum thermodynamics better, then that can have actually long lasting implications. Most of the electrodynamics or most of the things that we do in at this point of time is a result of our understanding about electrodynamics. And if you could understand strong interactions, if you could understand also the theory of strong interaction, then this can have actually far-reaching consequences, far-reaching implications. Like we can understand nuclear formation binding energies. At the moment, most of the nuclear physics is based on effective theories, where we assume that okay, there are certain effective degrees of freedom, we can describe their interactions. But we know that QCD or quantum thermodynamics is more fundamental theory. So if we could really handle this fundamental theory, we can understand why these kind of particles exist, how they interact between each other to form nucleus, how the various different binding energies that we observe can be explained based on theory, how we can actually argue what kind of new nucleus that we may not have observed can be actually formed, how certain things that we could not explain at the moment can be explained. Not just nuclear formation, we can actually also try to understand various details about star formation, supernova, neutron stars, quasars, etc. It's just a picture to give you how far the implications can go if we can really understand QC. Okay. Now the tricky part comes here. So we now sort of know that protons, neutrons, and electrons, of course, are the stuff of life. So anything that you see around are made of protons, neutrons, and electrons. I keep aside the electrons because we know that electron is so light that the total mass of anything that we see around is primarily determined by more than 99% of mass that we see around is mainly determined by protons and neutrons. So let's keep the electrons aside. We are not interested in the electrons at the moment. Let's just look at the protons. And I also said that protons are made of U quarks and D quarks. There are also other kind of quarks, but they seem not to actually play a big role at this point of time. Their role is there. That is actually a different subject. I am not taking that. But protons and neutrons, they are primarily determined by the U and D quarks. Now, if you look at the mass of proton, there is a unit called MeV, basically million electron volt. Electron volt is an energy scale for energy scale in terms of electron value, the electric charge, and the potential V. You can just take it as is for the time being. You can actually, if you want, you can actually assume this is basically kg. Okay. So proton mass is around 938 kg, let's say. Well, if you look at the U and D quark mass that are determined based on theory or some other determination, U quark mass is claimed to be only 2 kg, while D quark mass is claimed to be around 5 kg. Okay. Now I also said that proton is composed of 2 U quark and a D quark. Now if you add up the mass of these U and D quarks, basically comes to maximum of 10 kg, while the proton mass itself is around 938 kg, which means around 928 kg or 928 MeV is coming from something else that we don't know. That is actually the tricky part here, which means that most of the nucleon mass is not originating from BEH mechanism. I will explain BEH mechanism. I won't explain BEH mechanism, but I will just touch upon BEH mechanism in a moment. So you may have heard of Higgs discovery, the God particle, and it is actually argued that all the fundamental particles that has non-zero mass, the mass is coming from interaction of those particles or those fields with something called a Higgs particle or Higgs field, right? If these particles which originally did not have mass, they interact with the Higgs field, it acquires a mass. And this is that mass that U and D quark acquires when it interacts with the Higgs field. When I recall in my statement I said any particle, any fundamental particle gets mass from the interaction with the Higgs field. Proton is no more fundamental. Proton is a compact object or a composite object built out of U and D quarks. So that actually doesn't directly interact with Higgs field. So any energy that proton gets is primarily from some other source. BES mechanism is basically this Higgs interaction mechanism, standing for Gauss, Engler and Higgs. Okay. So if you look at the mass of nucleon, only 1% or less than 1% of the mass of the nucleon is primarily coming from BES mechanism, while 99% of the proton mass is coming from somewhere else. That is what we need to explain. And the origin of this is basically strong force, this quantum thermodynamics, and this is highly non-perturbative in nature at the scale at which nucleon exists. This is what I am going to explain in the next moment. So the next 5 minutes, this non-perturbative nature, what does it mean by that? What do you mean by that? So let's start with reanalyzing our hydrogen atom scenario that we have already talked about. We can consider the binding energy of hydrogen atom. To start with, actually hydrogen atom, we have a proton and an electron. Let's assume proton is fundamental for the time being with respect to quantum electrodynamics. Proton has a mass of around 938 MeV, while electron has mass of 0.5 MeV. If you look at the tables, you can actually see that this is just 0.5 MeV, which means that the mass of hydrogen atom is basically 938 MeV, approximately 938 MeV itself, because electron mass doesn't contribute much. Now, okay, I need to actually go far. So now, sorry. Why is it going the other way? Now, if you recall, the hydrogen atom binding energy was around 13 electron volt, which is like 10 raised to 6 magnitude lower than the mass of the hydrogen atom itself. Which means if you actually take a proton and an electron and compare its binding energy, the binding energy of electron is several magnitudes lower than the mass of the proton and electron. Okay, which means we have a theory. Where we can actually consider the binding energy as some small correction to the total mass. Or in other words, almost all of the physics that one learns in graduate school basically starts with solving exactly solvable problems. We take simple harmonic oscillator, we take some one-dimensional potential, we take even hydrogen atom. Okay, try to solve it exactly, and then anything that we could not explain, we try to argue that whatever we cannot explain is small compared to the original exactly solvable problem. Then what we can do is all these corrections due to something that we cannot explain are basically some small corrections or perturbative corrections. Okay, And so any theory that you actually approach, or any system that you try to approach using some assumption that the correction is basically some very small quantity compared to the original exactly solved system, is referred to as quadratic approach. Now here we have a scenario where the mass of the individual things are very small, while the correction to the entire system is very large. And this is a classic example of the case where whole is more than sum of its parts. Okay. So in a case where you can actually assume that these kind of corrections are very small, you refer to as means you use this approach called quantitative approach, or in other words, it's referred to as quantization theory. So you may have heard of this example in many places. If you don't know how to actually solve certain things, you start with assuming that this system is a sphere. Okay, here I actually took a case of spherical curve because this is something that you may have heard of. But if you want a bit more physics inside, you can actually think of the shape of Earth itself. You can think of Earth as a sphere, but it's actually not a sphere. There is some oblate or the other oblate or elongated stuff. You can actually add those changes from or deviations from the spherical form as corrections to it. If you take the same case here, you can actually assume that you have a spherical curve. Then you can actually slowly add some corrections, saying that okay, of course it has some small head, it has legs, it has tail, etc., etc., etc. And then on you can actually try to get better and better picture about what is going on. But in reality, the case that we are dealing with is actually a more complicated curve. You see actually the legs, head, etc. are sufficiently large compared to its size itself, right? Which means you cannot use perturbation theory. So a real curve really looks like this, and even after doing several approximations, you may not get perfectly the shape of the curve. Okay, and that's what I was trying to argue. So if you take the case of electrodynamics, if you add the mass of proton and electron, it's approximately 1 GeV. While the hydrogen atom binding energy is 13.6 electron volt, which is 6 orders of magnitude smaller than the mass of the proton and electron. Which means you can use perturbation theory in this scenario. Okay. While in the case of proton, you have 2 mu and 2 mu plus 2 md as a total mass of the constituents, which is around 10 MeV. While proton mass itself is approximately 1 GeV, which means you have some correction which is like 2 orders of magnitude larger than the mass of its constituents itself, and hence this is a heavily non-perturbative system. You have to use some non-perturbative approaches to actually tackle this problem. This much said, let's also get some feel of how these systems are actually studied in experiments before we really go into the theory or computation part. Many of these particles, like I said, protons and neutrons are not the only hadrons that we know of. We have now nearly 100 plus hadrons that we know of. Around 50 plus are forced-star or well-established hadrons, while many others are actually less established in the sense that they are given certain stars to identify how well they are determined. And 4-star means it's very well determined, lesser star means less well determined. There are many particles that are less well determined, which has some of them even have 1 star, which basically means whether they exist or not is not even sure. It's just that we found some signature in the experiment, and we hope that they really exist, and we will try to actually accumulate more and more information from the experiments. But it's not just from the experiments, we can also get information about the existence of millisect particles from post-nuclear showers, etc. Okay, first of those, these kind of particles were actually discovered in post-nuclear showers, not from the experiments itself, because we cannot access those particles unless we go at very high energies, and many of these particles were discovered in 1950s, and at that point of time we did not have that much high energy accelerators. So in the past it was mainly from post-nuclear showers, etc. While more recently we have particle accelerators, particle colliders, which are very high in energy. We can actually collide them at very high energies, which means we can access, or which means we can find out many other hadrons that might potentially exist in nature. And how do you identify them? So you basically collide, you take protons, accelerate them. You know cyclotron radiation, I assume you may have heard about that. If you don't know, you can actually assume that there are these charged particles. You can just put them in charged particles. You can just accelerate them in magnetic field and then make them collide at very high energies. When you collide them, they will just break apart, and following certain rules of quantum field theory, they will break apart and form newer and newer particles. Okay, and you get many other shower of particles. It's not just even single shower, multiple showers. Okay, and you actually look at these showers and try to figure out various correlations, etc., etc., and try to argue that these particles may have existed at this times. To be more precise, why I said all of these things is because many of the particles that we argue that these particles exist, some of these 1 star or 2 star particles, they are not observed as themselves. They are observed only from their final state fraction. So you get a lot of showers. Try to actually figure out various correlation between the showers that you actually observe in the experiments, and based on that you argue that these particles may have existed. Or in other words, this is typically in scientific language is referred as you look at the final state distribution, and based on the enhancement or dip in the final state distribution, you can argue whether a particle exists or not. While this sounds actually quite complicated, I will try to actually argue how you can understand this better. Okay, so this is one example. This is one very recent example. It's probably not the best example that I can show, but this is one of the most recent example. And since this is actually referring to a tetraquark, I thought actually this might be interesting. So there was a state that was observed in the experiments in 2020, where it was found in a 3-state final state combination. D, and D pions are basically mesons, as I discussed, these quark and quark kind of structures. So they found that actually there is a clear peak in the event distribution, which said that actually there is a particle with mass around this region. Okay. You can actually look into particle data group page to see what other particles are observed. While this might sound actually a bit difficult, let me try to give you a feel of what this is about, or what this discovery is, how we can understand this discovery from electrodynamics itself. I'm taking the example of electrodynamics because this is something that you may be more familiar with. It's nothing really new that you are actually doing, except that you are discovering new particles. Okay. I already talked about this hydrogen atom spectra, dimer, Padmanath, etc. I will not say the names, but hydrogen atom spectra I have already said about. What you do is you take a hydrogen gas, box of hydrogen gas, put white light into it, try to see what are the spectral lines that are either absorbed or emitted. Okay. When you actually pass the white light through the hydrogen gas, on the other side, you actually check which are all the spectral lines that are absorbed by looking at the dark features. While in the other case, if you actually look in the transverse direction, if these energies are absorbed, the hydrogen atom will later emit photons in arbitrary directions. So you can look in the transverse direction to see which are spectral levels or which are photon frequencies are emitted. From this, you can actually figure out what is the energy levels or what is the difference between the energy levels. This is what we talked about earlier. And to be more precise, what you look at is basically either the dip in the energy spectra of photons or peak in the energy spectra of photons. What is shown here is basically a hydrogen emission spectra, where all different frequencies are actually, so a spectrum of various frequencies are shown, while certain things actually have larger intensity. And intensity is proportional to amplitude square, if you are aware of. But this intensity is what I am interested in. Certain frequencies it has a higher intensity, and frequency is related to energy itself. Okay, and if you now look back into this figure, the x-axis is the energy of these states, and this is simply the intensity. Yield is basically the intensity. So you are looking at the intensity peaks in the final state spectrum. Okay. Now, if this is also difficult to understand, you can also think in terms of the resonance experiments, resonant column experiment that you may have done in your high schools or plus 2 level. You have a tuning fork, make it vibrate by hitting somewhere, keep it on top of your resonance column, change the length of the tube, and whenever the frequency of the tuning fork matches with the length, it starts to give you a sound boom, right? This is exactly what we also do. Except that our tuning fork, our resonance column is different. That's only different. These also, and this exactly why we also call these particles that we observe as this boom. It's also called as resonances, because they are so short-lived. You only see them as in terms of their finite states. You see some finite state distribution. You look at their correlations and try to reconstruct back what may have existed in the past. Okay. So now getting into more theory and what we exactly do. So now we have a theory where we know that we cannot use standard perturbation theory, where we cannot assume that we have a spherical curve, we have actually small perturbations, etc. So if you really want to attack this problem, then we need to actually do some non-perturbative approaches, and this is what we do. What do we exactly do? We know that actually QCD, we know the theory of QCD, or we know the action or the energy operators of the QCD. We define that on a discretized space-time grid. Why I take discretized space-time grid? That will be clear in a moment. But we actually define this theory on a discretized space-time grid. When I say discretized, I mean actually there is a spacing, that is space, means I have only discrete points in space and discrete points in time. And I define this theory on this discretized space-time grid. Okay? And then try to actually study this using computers. The reason is, like I said, this theory has a perturbative regime. I did not really say whether this has a perturbative regime or not. If you go into very, very high energies, your proton itself can get dissolved, and then it can happen that all these quarks and gluons actually stays free. In that regime, you don't have a proton to deal with. You can apply perturbation theory, try to describe what your theory is or what your system is undergoing. While at low energies where you and me live, we cannot use standard perturbation theory, and you have to go for some non-perturbative approaches. And in this regime, we have only some effective degrees of freedom that come out of some fundamental degrees of freedom, which simply doesn't add up to the total effective degrees of freedom. So you have to use the non-perturbative procedures, and that is what lattice QCD does. So lattice QCD, as I said, we consider a space-time, or else if you are not familiar with relativity, etc., you can also assume just space. We consider a space, we just discretize the space and put the theory on that space and try to simulate it. We know the driving principles of how this theory will evolve. We use those driving principles to evolve or simulate this theory on a computer. Okay? And we have these big machines where we actually put these kind of instructions and make it actually run through. And we get the solutions to the problems that we are interested in. Now these are basically referred to as Monte Carlo simulations, not random number based approaches. And this is not just unique to lattice QCD, this is widely used in many other fields of science, material science, chemistry, biology. I am not an expert to talk on those things. But one thing that I can definitely talk is that almost all of these studies basically involved a lot of statistical physics and data analysis. And many of the procedures that we use, although the physics that is aimed is slightly different, procedures that we have used are very much common across disciplines. That means a lot of prospects of communication between these fields exist in this kind of studies. Just that in our case, the scientific interest or the physics interest is that we would like to know how these effective degrees of freedom for protons, neutrons, other hadrons emerged from the fundamental theory where it originally did not exist. Right? This is what we are after. So these are some pictures of various of these other disciplines which I cannot explain at all. Some of them are some protein folding, etc. But this I can sort of say. Here what we do is we actually put in these instructions. We represent the system with set of numbers. We let the system, this set of numbers evolve or change as per the instructions that we give in. And this is some gradient or some picture of how this landscape look in a three-dimensional scenario. Okay, let me not go into those further details. Now some more technical thing. We just don't simulate things. I did not really talk about what physics we are interested in. There are multiple physics that we can do. I just list a small list of problems that I am interested in. Like there are many others who are actually using this thing. This is actually a very small group in the entire world. If you actually count the number of people who might be doing lattice QCD, for example, maybe I don't know some 20,000 or 30,000 across the world. Okay, which is a very small fraction. But if you actually just take LHCb, the CERN, the collider experiment, they themselves have more than 20,000 people. Okay, so lattice QCD, the entire community itself is probably 20,000 or maximum 30,000 is what I expect. So it's actually a very small community, but there are many different problems that people are trying to understand using these procedures. So whatever I discussed is basically Monte Carlo simulations of the theory. I put it in discretized space-time. Forget the second line. You don't need to look into that. As I argued, the whole part of my talk was trying to understand how proton mass and neutron mass emerge from this light for degrees of freedom. This is something that we try to understand. Not just proton and neutron masses. If you can do that, we can also try to understand how the mass of other hadrons that we know of also emerge from these fundamental degrees of freedom. Not just how the mass emerges from these fundamental degrees of freedom, we can also argue that what is the contribution of the U quark mass and what is the contribution of D quark mass. So what are other effects that actually contribute to, or if you can actually decompose the contributions of various components that drives the theory, so that your proton mass is around 1 kg. That you can actually try to understand, although there are certain technical and conceptual issues in it, but we can still get an idea of how you can actually figure out how quarks and gluons contribute to the mass and spin. You can also investigate what happens to these hadrons at very high energies. You can actually put in very high energies, very high temperatures, high magnetic field, etc. Try to understand what happens to these hadrons. Not just protons and neutrons, you can also deal with various other hadrons that we know of. If you don't understand this, forget it for the time being. It's not actually very important. Now, there are actually limitations for the procedures that we use. We can also utilize various theoretical formulations that we already have and something more that we need. You can use the new trend of quantum simulation, trying to use quantum computing procedures to simulate these kind of hadronic systems, try to argue what is probably happening to these kind of systems. Am I running out of time? No, right? Okay. So this is actually the cluster that we have at our institute. If you don't get any message, I just actually am giving you a feel of what is it that we have. If you just look at it, I'm not really boasting. I'm just saying that this is actually, if I just take the numbers and divide it by the number of users, I just have one CPU node, which means I have nothing. Okay. So in years to come, we will have probably 10 times more resource. Problem is actually India is relatively not that rich in terms of computation resources for pure science things. When you go to abroad, you can actually have much larger resources. Of course, actually India have much bigger computation resource for many other fields, also lattice. But whatever we have at IMSc is what I'm quoting. So in 2-3 years, we will have much more resource, near to approximately 10 times more resource than this. While we will not have 10 times more users then, this is what I assume, which means we will have enough resource by then. So we have some really big, so 150 TB is nothing for us, just to give you a feel. While you might know that actually your laptop may have 1 or 2 TB space, right, at maximum. Now, I will also emphasize why we need these kind of huge resources before I actually go into the next slide. You see, actually these are, when I said actually we put the theory in computer, what do you mean by theory? Theory is actually a set of equations or set of expressions. Okay, and these expressions we need to actually realize or represent them using numbers. And these numbers are basically some set of, these set of numbers are basically matrices. Or in other words, in a more technical language, these are basically a lot of path integrals or some integrals which you need to evaluate. And for each update you make, each evaluation you make, you need actually millions of flops, and you need to actually make such millions of updates, not one or two updates. You need to make millions of such updates, which means you need a really huge amount of resources. And some of these updates involve large matrix inversions. The matrices are of size standard to 8. I'm sure you may have tried to use some NP inverse or something, NumPy inverse, etc., where you may have actually put in some too close to matrix of size of 10 or maybe 100 at max, beyond which your laptop may have crashed, while we are dealing with matrices that are of size 10 raised to 8. So when I said 10 raised to 8, okay, this is actually, I'm really undermining the number of degrees of freedom. 10 raised to 8 is just one row, okay, which means you have 10 raised to 8 cross 10 raised to 8 matrix. While I say this, I should also say that I'm not so stupid to put 10 raised to 8 times 10 raised to 8 matrix blindly into a machine, because we have no machine in the world that can fit in this big set of matrix. So we make various manipulations so that we can still deal with this matrix without actually realizing the matrix. Okay, so there are techniques that we can deal with. Now, once again, when you actually do one such calculation, you are not done with it. You need to actually do various different statistical averaging, various different limits, etc., which I don't want to talk about. And just glimpse the team that I have at IMSc. You are actually, feel free to actually approach any of us, not just me, you can also approach students. We have also collaborations with scientists at EFR Mumbai, IISc Bangalore, various international collaborations. As Arjun has already said, I still have collaborations with people at the Kunstwerk Mines, Desi, Munich, Ljubljana, etc. These are my students, Babani Shankar Tribadi and Tanish. They both are in their 3rd and 4th years. I assume actually they will be able to answer anything at a student level in case if you feel difficult to approach me. There are also one postdoc who has already passed out from IMSc and another master's thesis student who is now doing a PhD at Cyprus. Okay, so now I will give you a summary and just conclude my talk. So I gave you a timeline of atomic theory, which actually explained that we have a rich atomic structure. They are not indivisible spheres. They have some rich atomic structure. Same way, protons is also clear. They are not elementary particles. They have some internal structure, and not just internal structure. Proton mass is clearly an example, a classic example of the statement by Aristotle. The whole is more than sum of its parts. It clearly means that if you need to understand the proton mass or how proton mass emerges from these fundamental degrees of freedom, you need really some non-perturbative approaches to actually deal with them. There are several others discovered hadrons, several others predicted by theory. I myself have predicted many, but they are still undiscovered because experiment doesn't have enough energy to reach those energy scales. Okay. There are several other candidates which are referred to as exotics because we predict them with some exotic properties that cannot be explained just based on some plain quantum mechanics, etc. Let's not discuss about those. And finally, I also talked about lattice QCD, the tool that we actually use to study these kind of things, these kind of systems. And this is actually a first principle tool where we actually put the real fundamental theory onto numerical, represent them with numerics and put them in computer to solve for this, solve and figure out their properties. And we have a rich big team at IMSc who does actually various these kind of address various these kind of problems. Yeah, with this I conclude. Thank you.
Does anyone have any questions?
Yes, yeah. No, not arbitrary. It should be colorless. In total, it should be colorless.
I mean, not full. Like, I mean, like, can we have some particle which has some, like, we have some red charge, right?
Yes.
So, do we have something like which has 3 by 2 green charge
Sorry?
minus half red charge?
No, at the moment actually we don't know. So this you are actually worried about the similar example for electric charges where U quark, P quark, etc. has fractional charges. These are you are referring to.
No, I'm just saying that if you have like that type of charge, then
Yes.
would the force be 0?
You see, actually, first of all, the reason why we impose that all these hadrons should be colorless is because we have never observed a quantity that has not shown color. Okay, this is actually primarily a theoretical constraint that we put on the system that we should be totally
I
colorless.
don't think.
No, let me complete this thing. So you have maths background, you have some group theory background.
Yeah, sure.
Okay, so so this is actually, this theory is basically an SU3 theory, and in SU3 theory, this is group theory. You can clearly argue which are the colorless combinations of different charges and which are colorful objects. Colorful objects we simply discard, and we just take the colorless realization to represent hadrons. Of course, even the colorful objects have some makes some sense in some regimes, but at least the things that I am discussing here, everything is colorless. So, not interested in anything that is colorful. We can simply realize all the colorless objects using the SU3 engine. This is what I am trying to say. Thank you. I don't know if that answers your question.
How does the force work?
Okay, so here I cannot really write down a plain potential because this is actually a more non-linear system. Okay, so are you aware of how we actually write down, get the potential from quantum electrodynamics to plain classical electrodynamics? No, so that makes actually it's a bit more difficult. So in strong interactions, it's actually a bit more complicated theory, where unlike in your electrodynamics, the force carriers can also interact with each other. Okay, in your electrodynamics, photons doesn't interact with each other. If at all they interact in some higher orders, which I don't want to talk about. But the interaction between the force carriers introduce some non-trivial physics into strong interactions. That means actually it's not easy to write down a potential. You can write down a potential in some extreme limits, but not in the regimes where we are interested in. Not in the regimes that we are primarily interested in. So a regime that I can immediately give you an example is, let's assume that your quark masses are very high. Okay, quark masses are very high, so you can actually write down your Hamiltonian as mass term plus a kinetic term plus a potential term. Right? You can assume that mass is so high that this quantity is the dominant term in the entire Hamiltonian. Let's assume that this mass is actually just taken out. Then you basically have 1 plus k by m plus b by m. Then you can actually just factor out this constant term and redefine your Hamiltonian. What is left is a 1 plus some small number and a small number. You can use what while here actually in the regime that we are talking about, your U quark mass is much lighter than the international. So you cannot do this kind of.
So, thank you, speaker.